Hi there, my name is Mike Conlan and I'm part of the Applied Snow and Avalanche Research Group at the University of Calgary, and I'm here to present some of my findings from my research topic. And the title is Measurements at Recent Deep Slab Avalanches, recent being ones that we visited within approximately 1 to 3 days post-failure. And this was presented at the 2012 International Snow Science Workshop in Anchorage, Alaska. So to start off, you can get the full paper at the ASARC webpage right here. As well, in fairly short amount of time, you should be able to get it on the ISSW webpage as well. So to start out my research, I had to define what sort of deep slab avalanches we were looking for here. And ultimately what came out of it is that we're looking for hard to forecast deep slab avalanches. So these are ones that fail after the avalanche cycles of a specific persistent weak layer. So let's say we had a surface hoar layer that was buried by a meter of snow, and then we had a widespread cycle 2 to 3 weeks after burial. Then I'm not interested in these avalanches because they're relatively easy to forecast because it's within the cycle. But then let's say one start zone fails 2 weeks or 2 months after that, after the avalanche cycle, then those are the ones that I'm interested in because they are deemed hard to forecast. So these are typically older than approximately 2 weeks for the persistent weak layer, and also they're typically have an average crown thickness greater than approximately 80 centimeters. And then for my grouping, I applied them as either natural, light trigger, or heavy trigger. So natural being any deep slab avalanche that failed without an external force applied to it. Light trigger being an avalanche that failed by either a skier or a snowmobiler, and heavy trigger being anything with a heavy force such as a helicopter, a snowcat, cornice fall, in sympathy, or something along those lines. So I'll quickly go through my methods and my data collection. So we accessed 41 deep slab avalanches, of which 9 were natural, 20 were light trigger, and 12 were heavy trigger. And as I previously stated, we tried to get through them as quickly as possible, and most were within approximately 1 to 3 days post-failure. First thing that we would do as we access them was we would look at the terrain. So we would gain some insight into the aspect, the slope, and the elevation. And then we would conduct a profile. And within the profile, we will look at different things such as bulk density by applying a tube through the snowpack down to the weak layer and then measuring the mass of that bulk density. We would also look at the hand hardness of the slab and the weak layer and the underlying layer. And then we would perform a magnitude of tests such as the deep tap test or the compression test. These numbers here indicate how many of the 41 avalanches we performed this test on. So we performed 17 deep tap tests at 17 avalanches, as well as 11 additional compression tests for avalanches that we went to prior to the inception of the deep tap test. 18 of the avalanches we performed shear frame tests, and we performed the propagation saw test at 21 of the avalanches. For the propagation saw test and the deep tap and compression test, we would do duplicates, and then for shear frames we would conduct 12 different shear frames and then average them. And we would also look at spatial variability where possible. So for example, at this one, we performed one profile at a representative spot of the start zone, and then we would perform multiple profiles in areas such as a thick spot and a thin spot along the crown. And we would always do it either 1 meter above the crown if it was deemed to be representative and to have not failed, so there weren't cracks around, and otherwise we would do it to the side of the flank. So these are the locations where the deep slab avalanches occurred. We have a couple in the coast mountains of British Columbia, and then the majority of the data is in either the Columbias or the Rocky Mountains of British Columbia and Alberta in Western Canada. So I'll briefly go over some of our findings now. Most of our access deep slab avalanches were either in alpine or tree line. We have such a high amount of tree line because they are typically safer to get to. But in reality, more deep slab avalanches occur in the alpine. Here's a plot of average start zone angle versus aspect. And what we see is that they occur on pretty much every aspect. And as well, the average start zone angle falls typically between about 30 and 45 degrees, which is a general amount for slab avalanches. And we also see a bit of grouping within the northerly aspect here, and this is possibly due to increased preservation of weak layers on northerly aspects. And we see that most of our access deep slab avalanches were destructive size 3. Another important aspect of terrain is thin spot triggering. We speculate that 7 of the light trigger avalanches were initiated in a thin portion of the slab. These are fairly easy to determine, as you can see the ski track going in, or you can talk to the people involved within the incident. And we also speculate that 2 of the south-facing natural avalanches were initiated in a thin portion of the slab, and this would be from solar radiation decreasing slab stiffness and then causing subsequent increased creep, and which could cause failure. And these are some of the pictures of the avalanches that we accessed last year. For the weak layers themselves, we found a variety of surface hoar, facets, and depth hoar, all with either a melt freeze crust or without. And we have a plot here now. On the x-axis we have the different ones, so surface hoar with the crust, facets with the crust and without, and depth hoar with the crust. And we plotted it against the weak layer age, and what we see is that surface hoar is generally less than about 60 days old, whereas facets and depth hoar can be quite a bit older. And what we also see here, somewhat interesting, is for practically all of these, we have a light trigger as the oldest, and this is likely due to late season excursions from backcountry recreationists. For hand hardness, we generally found the weak layer to be within fist to 1 finger, but also that the underlying and the overlying snow were typically harder than the weak layer itself. For deep tapping compression tests, we were consistently yielding sudden results, whether it be sudden planar or a sudden collapse. We also found a general increase as you increase the load. So with a deeper slab, we are finding generally more taps required to cause failure. And with our shear frame tests, we are generally seeing a higher shear strength as you increase the load. And also with the light triggered avalanches, we see a steeper trend line here, and intuitively this makes sense, as you would need quite a low shear strength to cause failure by the stresses induced by a skier or a snowmobiler in a very thick slab. For propagation saw test results, we were generally seeing less than 60% of the cut length, as well as propagation to the end of the column. With Dave Gautier's analysis, he found that less than 50% of the cut length meant high propagation propensity, but we speculate whether 60% may be a better value for deep slab avalanches. And we also see a weak correlation with load, and this is likely due to the fact that our data set is still quite small, and also that the slab stiffness properties are probably quite similar for most of these deep slab avalanches that we access. For spatial variability, we are generally seeing the same character across the start zone. So if it was yielding sudden releases in one area, it was also doing so in another portion of the start zone. For shear strength, we are generally seeing an increase of the shear strength as we increase the load within the slab. And also for propagation saw test results, we were generally plus or minus about 10% across the start zone and also yielding the same character. So if it was propagating to the end in one area, it was doing so in another portion of the start zone too. In the future, we plan on continually gathering data and specifically focusing on natural releases. We want to continue to look at the spatial variability across the start zone. We also want to include the preceding weather, so looking at the closest weather station and including things such as wind and precipitation and temperature. And ultimately, we plan on creating a decision support tool to help forecasters decide if they should be controlling for deep slab avalanches. And I'd like to thank our supporters of ASARC, as this research would not be possible without them. And I'd also like to thank all the operations that we were able to get to during this research, as their insight and logistical support is invaluable. Thank you very much.